Let's look at another example. This is a little bit different than the previous examples that we've looked at. In the previous examples, we've done circuit analysis to come up with a frequency response, or we've been given the mathematical expression for the frequency response and been asked to come up with the Bode magnitude plot. In this problem, we're going to take a look at problem 9.21 here. We actually start with the Bode plot, and we're asked to find the transfer function or the frequency response. This would actually be the first step in the design process, actually. So going in the opposite order, where we would start with the Bode plot, come up with a transfer function or frequency response, and then the next step would be to actually come up with a circuit that then has that corresponding transfer function. So in problem 9.21 here, says determine the voltage transfer function h of omega corresponding to the Bode magnitude plot shown in this figure. Figure's on the next page. So that Bode plot looks like this. Let me drag it over here to the right of my screen so that I can see it. So now I've got both it and my whiteboard available. So again, this is example, and it's problem 9.21. Okay. So we can see from the components of the Bode plot here that there's a 0 at the origin. This line again would extend on forever toward omega equal to 0. So in terms of the components, we have a 0 at the origin, and then offsetting that 0, we've got a pole term at omega equal to 1. This 0 term would continue on forever, but there's a pole term here that would be going downward, so that means that the graph actually levels off. So we have pole terms at omega equal 1, and then we have another pole term at 100 radians per second. These are given in omega. And then assume this line then continues on forever. So that's enough information to allow us to actually construct the transfer function. We'll throw an arbitrary constant in here, k. This will allow us to shift the graph up and down. And then the simple 0 at the origin is just a j omega term. Okay. And then we've got the two pole terms, 1 plus j omega over 1, and then 1 plus j omega over 100. Okay. So this is the rough form of our transfer function. The only thing left to do is actually determine the value of this k, that would shift this thing up and down. Well, if you recall, for frequencies less than 100, this term is equal to 1. For frequencies less than or equal to 1, this term is also equal to 1. And if you remember, our simple 0 term would actually cross 0 dB at omega equal to 1. So if k is actually equal to 1, this peak value here would actually be 0 dB. We see that instead of it being 0 dB, it's actually 26 dB. So k here has to be this offset that would shift this entire graph up from 0 dB, which it would be if we were just graphing this, up to 26 dB. So k in dB is 26 dB. And so that implies that we know that 20 log then of the linear value of k is equal to 26. So turn that around. Log base 10 of k would be 26 over 20. And the inverse function to the log base 10 is just 10 to the power. So k would be 10 to the, well, that doesn't look much like a 20, does it? That's 26 over 20. 10 to the 26 over 20. And you evaluate that on your calculator, and it turns out to be 20. So the complete transfer function for this is just 20 j omega, and then I'm going to write this as 1 plus j omega, and then 1 plus j omega over 100. Okay, and that's our answer, actually. Whoops, sorry. Got a little sloppy with my drawing my box around my answer here. So that's it for this video. I want to come back and want to start the next section on passive filters. And so I've got a couple more videos that I want to do on the next section.